Hi, welcome to part 2 of the 20sim animation window tutorials. We've been working on a single pendulum, and in the previous video we did a line animation of this pendulum, and I used a bond graph in which the absolute velocities of points such as the center of gravity G and the hinge point A, they were expressed in components in the fixed inertial frame. And if I integrate those velocities, I can get the position of point G, x-coordinate, and y-coordinate. And we inserted a line into the 20sim animation window. And we just drew a line from 0, 0 to xg, yg. Okay, and just a note before we continue here. If you had used an Euler junction structure, and if you had expressed the velocities of the points on the body in components in a rotating body fixed frame, okay, so if you'd used body fixed coordinates, and if vgx and vgy were the absolute velocities resolved along the body fixed frame, you couldn't just integrate those to get the positions of the center of gravity. You'd have to transform from the body fixed frame to the inertial frame and then integrate the velocities with components in the inertial frame in order to get the position. So this will make sense to those of you who've used some body fixed coordinates before. So what we're going to do now is we're going to go back to our simulation window. So here's the plot of y versus x of the center of gravity. I'm going to go back to my 3D animation window from before. So here's the line that we had added. If I do Control click and move my mouse pad or my touch pad up and down, I can zoom in, and Shift click and up and down on the touchpad will let me pan around. Okay, so I'm going to double click on the 3D animation window, and I've got a line in my reference frame. I'm going to go up to reference frame, right click, and insert I'm going to insert a cube this time. So I'm going to insert a rigid body. I'm going to put the origin in the center of the cube. I can put it in the bottom or on a corner. I often find it convenient to just use the center. So the origin is going to be at point G. And I'm going to scale it such that the x dimension of the pendulum is the length of the pendulum, so 1 meter. So that should be a value of 1 meter. I'm going to make it thinner in the y and z directions. So I have a 0.1 meter square cross-section pendulum that's 1 meter long. I'm going to make it, I'll make it red. And I can import textures, I can apply transparency, and I can basically make it completely opaque or transparent. So you can play with all these different drop-down options. Okay, so now I'm going to make the x position equal to xg, the integral of the velocity of point G in the x direction. So I'll go back to my pendulum submodel. I'll go to xg, I'll take that as the variable for the x position. For the y position, I will take the output of the yg integrator, and I'll make the z position 0. And when I press OK here, I have a body, a block. Okay. So now when I run the simulation, what's going to happen is, okay, it ran almost instantaneously. When I play back the animation, I see the position of the center of that body moving as it should. However, the orientation needs to be adjusted. So with the line, I was just connecting 2 points. With the body, I've got the center of the body moving along the right trajectory, but now I need to constrain it so that the angle of this body, there we go, I finally got Control click working to zoom and Shift click to pan, and I should be able to, if I just click and then move my touchpad, I can rotate, and now I can sort of get a sense of the cross-section of my beam there. Okay, so I'm going to go back to my front XY camera, so I'm looking straight on. Okay, now how do I, oh, that didn't quite do it, did it? So 3D animation, front camera, and I'll hit OK. And for some reason I need to set the values of that front camera back to 0, 0, 0. Actually, nope, not happy with that either. Let me just go back to, I'm just going to do this manually. This is a bit of a tricky aspect of this, I must say. Alright, so right now I've got X and Y there. I'm going to zoom in and out, or pan with the Shift key, and zoom with the Control key. Alright, so once again I've restored the simulation that I had previously. Okay, great. So now, orientation of this thing. I'll go back to my model. Now I've taken the angular velocity and I've integrated it to get angle theta. Now because this is a rigid body, I need to define something called an orientation matrix here. If I double click on the block that I just brought in, and if I go into, I think it's not color, there's somewhere I can go here where I can show the reference frame. Okay, let me see here. Orientation, object properties, set object properties. Okay, I don't see it in there. Oh yes, okay, if I highlight block here, if I go down and click show frame, there's a body fixed frame associated with any rigid body you bring into 20sim. So right now, there's a body fixed frame, XY, that's attached to and rotating with this block. Now what I need to do is I need to define the rotation matrix that would take me from the body fixed frame of this block to the inertial frame. So what that means, in a nutshell, is I'm going to go back to this little sheet here and do a drawing to try to explain this as simply as possible. Okay, so suppose I have, call this rotation matrix. Imagine I have a fixed XY frame. Okay, so I'm going to have a unit vector I going that way, unit vector j going that way. Suppose I have a triangular link, and that triangular link is sort of pinned at the origin. And now suppose I define a body fixed reference frame. I'll call this x1. Oops. Call this x1. And I'll have another, I'll have a perpendicular direction y1. So x1, y1 axes, they rotate with the body, and they will acquire an angle theta defined positive counterclockwise from the horizontal. Now suppose I have a point somewhere on this link, and I'm interested in the position vector of that point, which I'll call r. And suppose I want to express r in components in the body fixed frame. So let's say I've got a distance x, and let's say I've got a distance y. Okay, so if I'm rotating with this body fixed frame, then the position vector is xy in the rotating frame. However, I know that the absolute coordinates of the endpoint of that vector are not just x and y. They need to be transformed somehow if I want to get the coordinates or the components of this vector in the fixed I and j directions. Okay, so what is this vector? This vector r is its x in the rotating I1 direction plus y in the rotating j1 direction. And if I take a close look at those unit vectors, here's I and j, and then I have I1 and j1 separated by an angle theta. If I take the rotating I1 vector and drop a perpendicular to the I and j axes, that I unit vector with length 1 is going to be cos theta I plus sine theta j. And I can take a look at the rotating j vector. That angle is also theta. And I can say that j1 vector, it has a negative I component. Magnitude is sine theta. It has a positive j component. Magnitude is cos theta. Okay, so I can transform vector r. I'll use a left superscript here to indicate that it's in terms of the rotating frame 1. I can express that vector in the inertial frame by just subbing in the expressions for those unit vectors. So I'll go back to the blue pen here. Okay, so r in frame 1 was x and y if I express it as a column vector. Vector r in frame 0, the fixed inertial frame, its I component is going to be x times rotating I, which gave me a cos theta, plus y times rotating j, which gave me a minus y sine theta. That's the I component, the fixed I component. The fixed j component is going to be x sine theta from x rotating I, plus y cos theta from the rotating j, y cos theta in the j direction. Alright, so I can now express vector r with components in the inertial frame as a matrix multiplication. Cos theta minus sine theta, cos theta, sine theta, cos theta, multiplied by x and y, which was the vector expressed in rotating frame 1. Okay, so this little matrix here is called a transformation matrix. And it may be of interest to note that this first column here, cos theta, sine theta, that gives you the components of the rotating I1 unit vector. It gives you the components of that rotating unit vector in the fixed frame. So the rotating I vector, if we go back up here and take a look, the rotating I vector, this one, is cos theta I plus sine theta j. So cos theta I, sine theta j. If I go the other way and look at a row of this vector, okay, that cos theta minus sine theta, those are the components of the fixed I vector in the rotating frame. Okay, so the fixed I vector is cos theta rotating I minus sine theta rotating j, as we've already concluded. Alright, now if I carry this one step further, I can treat this as a 3D vector transformation. Okay, so really the R1 vector is x, y, 0. And the the same vector in the inertial frame is x cos theta minus y sine theta I, x sine theta plus y cos theta j, plus 0 k. So I'm going to add a page here. And on the next page, bearing in mind that each of these columns is the components of a rotating vector in the fixed frame, I'm going to write the 3D transformation matrix that relates R0 and R1. So R0 is going to be, if I add the z component, I'm going to have cos theta, sine theta, and 0. So those are the components of rotating I in fixed frame 0. There's no z component. I'm going to have minus sine theta, cos theta, 0. Those are the components of the rotating j vector in fixed frame. There's no z component there. And the rotating and fixed unit vectors in the z direction are the same. So because this is in 2D, the rotating k vector and the fixed k vector are aligned. So the components of the rotating k vector are just k, 0, 0, k. Alright, so there's a 3D transformation matrix. And what I can do with that is I can take a vector in the rotating frame, multiply it by this transformation matrix, and get that vector in the fixed frame. So sometimes you might see that called R01. So R in frame 0 is R01 times R in frame 1. Okay, so we have a vector R, which in this case is conveniently expressed as xy in the rotating frame. The rotation matrix lets me express that vector in the fixed frame. So how am I going to use this in my 20sim animation? Well, I'm going to go into my theta subblock, and I'm going to define that rotation matrix because the 3D animation window wants that. Okay, so here, parameters, I'm going to declare a variable, and that variable is going to be real R01. I'm going to make it 3 by 3. And then down here I'm going to say R01 equals, I'm going to have cos. Okay, so this is the block that integrates omega to get theta. So the default output variable for an integrator block is just called output. So I'm going to say that my rotation matrix is supposed to be cos theta. I'm going to say cos output. The next term is minus sine theta, so I'll go minus sine output, 0. Next row of the vector is sine output. Sorry, next row of the matrix is sine output, cos output, 0. Then the final row is 0, 0, 1. And now when I check the submodel, I get no errors. So now I have a rotation matrix. Okay, let's go back to our 3D animation window, which was window 3. Okay, double click on 3D animation. Under my block I've got the position defined properly. Now I click the orientation tab, and I can choose a number of options. One of them is rotation matrix. So I'm going to click choose rotation matrix. I'm going to go into the theta subblock. And sometimes you'll see this expand matrices or vectors clicked, in which case it breaks it up into components. I want to unclick that and choose the entire matrix. So there's my rotation matrix. So now I go down and click OK. And now when I run this simulation again, it should orient the body using that particular rotation matrix. And here we go. You can see the body fixed XY frame is moving with the body. So when it asks you for a rotation matrix to orient the bodies that you bring in, it's looking for the rotation matrix that takes you from a vector expressed in a rotating frame to the same vector expressed in the inertial frame. So here's that rotation matrix for this particular example. Okay, more complicated than for the line drawing, but especially when you get into 3D animations, it's nice to be using the bodies instead of the lines. Okay, I hope that was helpful. Thanks for watching.